My pleasure. And I must say, I've been really impressed by all your questions. It showed that you did prepare and read papers and think about it.
Thank you.
And that's very much appreciated. Thank you.
Today is an incredibly special occasion. We have Professor Yoshua Bengio on the show. I just can't get over it. But first of all, a little bit of housekeeping. So we've just launched a new Discord community. So please jump in there, say hello, introduce yourself. If you want to be, part of the moderating community or just help us do stuff over there, we would love to talk with you. By popular demand, we've also added a couple of ways in which you can support us. So we now have a Patreon and a merch store. If you're interested in supporting some of the episodes of MLST, then get in touch with us because we'd love to have a conversation with you. We're just doing so much cool stuff this year. We've already recorded about 6 episodes that we haven't released, and we've got some amazing people booked as well. So yeah, it's going to be incredible. As always, if you like the content here, please consider hitting the like and subscribe button and rating our podcast on iTunes because it really, really helps us out. I called it iTunes. Is it iTunes? Apple Podcasts? I don't know, whatever it's called. Weights and Biases is the developer-first MLOps platform, and we're extremely proud today that they are sponsoring this episode. Now, tracking machine learning experiments is difficult. Using the winging it methodology can only get you so far. What we need is a platform where we can compare models and visualize their performance characteristics against all of the previous runs and figure out the best hyperparameters to use. Now, most importantly of all, this process needs to be reproducible. Sounds like a tall order, right? Well, this is exactly what the Weights and Biases platform does for you. Now, you can even follow metrics from long-running experiments in real time. I think it's really important to lean into the complex interaction between science and engineering in the ML DevOps lifecycle. Data scientists need valuable feedback, and they need to communicate why they're running given experiments, and they need to share their notes around the next steps. Reports keep this work well organized and connected to the Weights and Biases experiments which were run, as opposed to just sharing random screenshots in Slack. It's so easy to create a report and share it with your team after you've finished with your experimentation. You could just add notes for yourself as well to explore later on. You can keep a work log, and you can even share your findings internally or externally. This is an absolute game changer. I'm a big believer in this kind of engineering rigor. I'm the CEO of a code review startup called Merge these days, and I love how the pull request process and tooling immortalizes important collective decisions which were made during the software development lifecycle. Similarly, Weights and Biases immortalizes important decisions that were made during model development, experimentation, and deployment. Remember, check out Weights and Biases today by going to 1db.com/MLST. And if you're interested in sponsoring future episodes, get in touch with us. Weights and Biases are currently sponsoring our premiere shows, but we have lots of other content coming and opportunities for sponsorship, so let us know. Cheers. Professor Yoshua Bengio has just released a bunch of papers around GFlowNets. Now, GFlowNets exists squarely in the domain of active learning, which is a model that can economically ask an oracle, which is probably the real world, for the most salient training examples to continue learning. The learner can choose or have an influence on the examples it gets, and we want to learn a function which approximates the oracle efficiently. How should we pick the queries? How should we take into account not just the value of the predictor, but also how certain we are about the predictors from the learning system? Areas of uncertainty or entropy are kind of like interesting candidates for us to explore further. We need to be able to imagine or invent queries to give to the oracle. Now, one of the reasons that machine learning models are so sample inefficient is because of the combinatorial space of possible input examples. We can't train on everything because the space is just too large, it's vast. So you might have heard of a related concept of active learning called machine teaching, which is an interactive version where the human interactively selects the most salient data to train a machine learning model, maximizing the information gain in respect of the training samples. Now, the reality is the function space that we're learning here is highly structured. we only really need to sample training data where most of the rich information exists in that function space. I mean, if you think about it, a machine learning model, it's just a joint probability distribution between signals and labels. And this distribution has modes or areas of density or information. And actually, most of it is just areas of nothingness, which require fewer training examples to learn and to represent. Now, if you spoke to a Bayesian person like my friend Connor Tan at work, how to learn this distribution, they would bring up Markov Chain Monte Carlo quicker than a whippet with a bum full of dynamite. Now, Markov Chain Monte Carlo is an increasingly popular sampling method for obtaining asymptotic information about unnormalized distributions or energy functions, especially for estimating the posterior distribution in Bayesian inference, which is where you've probably heard of it before. Now, you can characterize a distribution without knowing all of the distribution's mathematical properties, so if you don't have an analytical representation for it, just by randomly sampling values out of the distribution. Now, a particular strength of Markov Chain Monte Carlo is that it can be used to draw samples from distributions, even when all that is known about the distribution is how to calculate the density for different samples. Now, the Markov property of Markov Chain Monte Carlo is this idea that random samples are generated by a special sequential process, and each random sample is used as a stepping stone to generate the next random sample. Now, this might sound very complex, but the practical implementation is pretty simple. Markov Chain Monte Carlo just starts with an initial guess, just one value that might plausibly be drawn from the distribution, and then we produce a chain of samples from this initial guess by adding random perturbations in the neighborhood of that example. And each new proposal drawn from that random perturbation distribution is either rejected or accepted. There are different flavors of this, of course. I mean, in particular, like tweaking how the random proposals in the neighborhood are selected or whether the proposals are selected. The simplest heuristic being whether it's below the function or not. Now, the idea is that Markov Chain Monte Carlo methods, they capture a distribution with only a relatively small number of random samples, but the reality is anything but. In high dimensions, and where the distribution has many modes spread far apart, it's actually exponentially expensive. There's a bunch of human-orientated hacks to try and make this work well in specific cases, but we're missing a much more general machine-learnable solution. This is the main reason why we haven't seen it used in many machine learning applications yet. Assuming that the function we want to learn has underlying structure, then we can escape the exponential time of Markov Chain Monte Carlo with machine learning. And this is what Bengio calls systematic generalization, which is to say, how do we generalize far from the data in a way which is meaningful? Now, GFlowNets are an active learning framework where the name of the game is to generate salient and diverse training data to augment our model in the most sample-efficient way possible. For GFlowNets to work, we need a reward function and a deterministic episodic environment. Does that sound familiar? Yes, just like reinforcement learning. Now, a flow network is a directed graph with sources and sinks and edges carrying some amount of flow between them, through intermediate nodes. So I think a good way to think about this is pipes of water. Now, for our purposes, we define a flow network with a single source. So the root nodes, or you might say the sinks of the network, correspond to the terminal states. Now, it's designed to find the possible trajectories through our system, okay? Just think of AlphaZero as being like a good analogy for these trajectories. Now, the training objective is to make them approximately sample in proportion to the given reward function. This is in stark contrast to AlphaZero, where we were sampling to maximize the expected reward. So Bengio's big idea is that we could have an interacting loop between a generative model and the real world. The real world is expensive, so why not train an imagination machine in our mind until we're ready and waiting to produce good questions to the real world? We could use imagined experiments to train our generator, then produce queries to the real world.
We were thinking about a way to visualize how GFlowNets work when the idea of a Galton board came to mind. A Galton board, also known as a beam machine, is a common prop in statistics courses, science museums, and fun gadget stores. The board has rows of interleaved pegs above a bottom row of buckets. Beads are filled into a funnel at the top of the board and then sprinkled on the top center peg. The beads bounce either to the left or to the right as they hit the pegs and eventually collect into buckets at the bottom. If the pegs are precisely and symmetrically arranged, the beads will aggregate at the bottom into a familiar binomial bell curve. Now imagine that the pegs were instead flow gates with adjustable valves that could direct the beads more to the left or more to the right to bias the flow paths. With such a machine, you could adjust the valves or flow rates to create any distribution. For example, to create a uniform distribution, we'd open up the gates flowing away from the center line of the board to drive more bead flow to the fewer number of paths leading to the edges and the corners. Or to create a multimodal distribution, we'd arrange the gates to split the flows into two or more streams that would then pile up in multiple humps or modes below. There's a lot of flexibility here. Indeed, given a distribution, there are generally multiple flow gate solutions to produce it. It'd be nice, wouldn't it, if we had an intelligent, principled way to train these gates. Enter GFlowNets. GFlowNets put a neural network, a brain, behind the flow adjustments. A brain which can optimize the gates to match any distribution we desire. Here we are interested in sampling a reward function in the context of reinforcement learning. In that context, this is a powerful simulation and sampling paradigm. You see, once the brain has tuned the flow weights, such a modified Galton board, or more generally a flow network, can sample diverse paths quickly and efficiently, leading to the reward distribution. It's important to point out that the path sampling is more diverse doing it this way. Unlike classic reinforcement learning, a GFlowNet doesn't just fixate on a small number of high-reward paths it happens to find first. Instead, it stochastically samples a broad spectrum of paths in proportion to their reward. Sure, high-reward paths will be sampled with higher weight, but the far larger population of low-reward paths will get a share of the sampling as well. Why should we even bother with such paths? The answer is we need to balance exploitation or high reward with exploration or learning to better learn the reward function. This is especially important when dealing with complex, real-world scenarios of high uncertainty. For example, think of molecular drug discovery and design, or navigating jungle terrain. In both those scenarios, we really know very little about how a particular path may play out. We might stumble into the next miracle cure or a pitfall of quicksand. To find the globally best paths, it's important to keep our options open. Beyond this sampling diversity, GFlowNets also bring the full power of neural networks to discover latent structure and learn the reward function. This, combined with their diverse sampling, also makes GFlowNets more robust when dealing with multimodal distributions, which are a common trap for greedy algorithms and Markov Chain Monte Carlo. If there is structure linking the multiple nodes, GFlowNets can learn it and extrapolate to new modes, and once discovered, they will, by design, drive the sampling to cover those modes and learn more structure. Overall, GFlowNets seem to offer an intriguing new path, pun intended, for an intelligent sampling paradigm.
So you might ask, how are GFlowNets different from AlphaZero? Well, the policy network in AlphaZero gives you a set of actions given a state. AlphaZero trains the policy network to maximize reward so that the trajectories all end up at the highest reward. Now, what GFlowNets do is they train so that the actions are distributed in proportion to the reward. So rather than pruning away all of the low reward trajectories, it will sample them just less often. Now, there is a manifest difference between GFlowNets in respect of exploration. I mean, you might argue that the Monte Carlo tree search is still doing wide exploration at the beginning, but in spite of its rapid convergence and pruning of low reward trajectories, it's still sampling from the underlying probability distribution, which has been scaled with a softmax. So there's actually not that much to explore in the first place. So in summary, GFlowNets are better than AlphaZero and Monte Carlo tree search in some sense because they achieve the same goal by offloading the burn-in time and the stabilization time of Markov Chain Monte Carlo. Remember, this whole thing can be trained offline, and then when in inference mode, we can do it in a single shot. Whereas with Monte Carlo tree search, we actually had to do it in inference mode as well. The other thing is we're kind of offloading all of the human engineering required to sample efficiently from Markov Chain Monte Carlo. And the other thing is diversity, baby. I mean, consider the difference between how GFlowNets and AlphaZero sample the reward path distribution. If you looked at the distributions, you would see that AlphaZero has a little box around the mode. GFlowNets is the whole distribution. We know very well that diversity preservation is critical in order to discover interesting stepping stones in search problems. Now, finally, Bengio has published results showing that GFlowNets converge exponentially faster than Markov Chain Monte Carlo and PPO on some problems, and finds more of the modes in the distribution function faster. Enjoy the show, folks. Professor Yoshua Bengio is recognized worldwide as one of the leading experts in artificial intelligence, indeed, a godfather of deep learning. His pioneering work in deep learning earned him the Turing Award, which is the Nobel Prize of Computing. He's a full professor at the University of Montreal and the founder and scientific director of Mila, which is a prestigious community of more than 900 researchers specializing in machine learning and AI. He's one of the most cited computer scientists on the planet, and I can't even begin to articulate how honored we are today to have this conversation. Yoshua has done a lot of work recently on GFlowNets, which are an active learning framework in a reinforcement learning configuration, where the name of the game is to request salient and diverse training data from the real world to augment our learned models in the most sample-efficient way possible. Now, we're trying to minimize the divergence between the path distribution and the reward distribution, and then sample paths according to the reward distribution. This is in stark contrast with traditional reinforcement learning, where we're trying to maximize the expected reward. This approach is likely to find diverse strategies instead of being greedy and converging quickly after finding a single one. Anyway, Professor Bengio, this is amazing. Can you tell us about this exciting work and some of its applications?
Yeah, I don't think I've been as excited about a new topic, at least in the last 6 or 7 years, as I'm now with GFlowNets. And it's actually even much more than what you've been talking about. The way I think about GFlowNets is a kind of framework for generic learnable inference for probabilistic machine learning. So one way to think about this is it's a learnable replacement for Monte Carlo Markov chain sampling. But actually, so there's that, and I'll explain, if you want, why this is important and to use machine learning there. But also, it can be used to estimate probabilities themselves. So not just sampling, but also estimate intractable quantities like partition functions and conditional probabilities that would otherwise require summing over an intractable number of terms. So I think of this as these potentially, if there's still we're still at the beginnings of this, as a Swiss Army knife of probabilistic modeling that uses machine learning to be able to do things that look intractable, but do them efficiently thanks to generalization power of large neural nets.
We've been trying to think of a way to help our listeners visualize what a GFlowNet does. And I wanted to run by a possibility to you. So I'm not sure if you've heard of Galton boards, also called bean machines. And what they are is this prop that's often used by statistics professors at the start of, say, an elementary introductory course to give a visual intuition. And it's a board that has these vertical buckets down at the bottom with interleaved rows of pegs above the buckets. And then beads are filled in into the top of the board, and they bounce either left or right as they hit the pegs, and they eventually collect down at the bottom.
Yeah.
Now if the pegs...
It's a very good analogy, except that it's not a tree. I don't know how these things are, but the ball can come to a place from two different paths, or in a potentially large number of paths.
Right. And I think given there are some differences, the idea was that if the pegs are...
No, it's pretty close to exactly what it is.
Yeah, and what we were thinking is that if the pegs on the Galton board are precisely and symmetrically arranged, the beads will form a nice binomial curve at the bottom. And it seems like what GFlowNets are capable of doing when they optimize the path weights, they're tweaking the pegs a little bit to the left or a little to the right to bias the flow of beads one way or the other. And in this way, a GFlowNet could arrange the pegs so that the beads could form any distribution at the bottom that we want. And for our purposes, that means a distribution that matches the reward function. So is this a good way to think about GFlowNets?
Yes, it is. Now, it's missing a really important aspect of it, which would be difficult to present visually, but that all of these peg weights, like the probability that the ball goes left or right, are not just like learned independently, like as a tabular machine learning, but that there's like one neural net that knows about the locations in this big board as input and tells how much relative weight should I go left or right at this position. So the reason this is important is because it allows for generalization, because this board is huge, it's exponentially large, right? So there's no way you're going to learn like a separate parameter for each of these choices. And so you have this neural net, or potentially several neural nets, but that allow you to share statistical strength, as we call it, share information across all the possible positions so that it can generalize to places, paths that it has never seen from a finite number of training trajectories that it sees while it's being trained. And that's crucial, otherwise you couldn't scale to large problems, which is really what we want to do.
Professor Bengio, we spoke with Professor Carl Friston about his free energy principle and active inference, which is pretty much a Bayesian flavored version of reinforcement learning. And he said that while we need to maintain entropy and stop models from increasing too much in complexity, we should balance entropy with accuracy in a principled way. And by the way, you can kind of think of, just to the audience, think of entropy as keeping your options open. But Friston thinks that the Bellman-esque idea of reinforcement learning, which is to say maximizing expected reward as the objective, is misguided, and we should instead perform inference over future paths, balancing expected reward with relative entropy. Is there a connection between these ideas? It seems like GFlowNets are sampling paths proportional to the reward function that will maintain as much entropy as the reward function itself. Yes,
exactly. It's a translation of the reward function into machinery that can sample, the equivalent, the corresponding distribution. So yeah, I completely agree with what Carl was saying here. But as I said, what's interesting is we can do things with GFlowNets in principle. We've done the math and some small-scale experiments that we have now a number of papers. We can do things that go beyond sampling. But, for example, estimate entropy itself. So entropy is notoriously difficult to estimate. And I mentioned in my talks on GFlowNets that we can use the GFlowNet machinery to estimate entropy of, say, an action distribution or a distribution over Bayesian parameters, for example, which would be something you'd like to minimize if you're going to take an action in the world and you have a model of the world that has uncertainty, and that connects a lot with Carl Friston's interest. You'd like to be able to choose an action that minimizes your uncertainty about how the world works. What are the latent things that may have happened, and an important part of that is estimating the reward for these exploratory actions, like children playing around, is how much reduction in entropy of my knowledge of the world am I going to get through that action. So you need to be able to compute that reward. And that reward is basically an entropy over something you care about. And it turns out you can also do that with GFlowNets.
We're actually speaking with Tristan again next week. Do you have a question that you would like us to put to him?
Well, he's on the biology side of things much more than I am. And I believe there are amazing scientific opportunities to explore how the kind of machinery that GFlowNets offer could be used by brains in order to do some of the things they do, using neural nets to model the probabilistic structure of the world, including uncertainty, which is something he cares about, but also taking into consideration things like high-level cognition, the global workspace theory, which is something I care a lot about, attention. They all kind of fit in the picture of GFlowNets. So I think there's a huge potential of research at the synergy of computational and theoretical neuroscience and machine learning, probabilistic modeling of the kind that GFlowNets propose to come up with some proposals for explanatory theories about what the brain does that's probabilistic. And, I think he would be a great person to be part of that thinking.
Fascinating. Well, going a little bit further down that line, there are folks in the community who are huge advocates of biologically inspired approaches to machine intelligence. And, one of the key ideas actually is diversity discovery and preservation, both in how knowledge is acquired and represented. I mean, specifically evolutionary algorithm advocates. They differentiate themselves from gradient-based single-agent monolithic approaches like reinforcement learning. And they point out that their approaches overcome so-called deception and search problems, which is to say they don't get stuck in local minima. Your approach seems to be achieving something very similar in the context of a gradient-based reinforcement learning package. I mean, I don't see it as being mutually exclusive, but what's your take on this?
Yeah, diversity is important when you're exploring, and humans, especially young ones, are exploration machines. They're trying to understand how the world works, and they're acting in the world in order to get that information. Yeah, I agree that that search process needs to have a big bonus on diversity, like on trying different ways of achieving something good, like better understanding how the world works. So it turns out that in the GFlowNet framework, you have a training objective that yields this kind of diversity and exploration, but is based on training large neural nets end-to-end. Now, it's a bit different from the usual end-to-end training because we don't have an objective. The objective we're trying to optimize is not tractable, actually. But we can sample these trajectories, which I think of like sampling thoughts. Like our thought process is going through some chain of explanations. It's not a complete, and it doesn't represent all the explanations. But what we found with our training objectives for GFlowNets is that these sort of randomized kind of views of the world are sufficient to give a training signal to the neural nets that do the real job.
Yeah, I'm curious. So this trade-off between exploration versus exploitation, and this has come up in so many contexts, throughout our show. And one in particular is we've talked to multi-arm bandit folks, right? And GFlowNet seemed to capture this balance between exploration and exploitation. But the multi-arm bandit folks, they dive deep in that research circle into this trade-off. And I think they have some very principled ways and even very rigorous ways to analyze this fundamental trade-off. To what extent do you think that their research maybe could be applied to future GFlowNet variations? Like, do you think maybe it might open up more options to fine-tune the trade-off between exploration and exploitation?
Yeah, I mean, the bandit research is very, very closely related to the GFlowNet thread. The GFlowNets, as we have been using them, for example, for drug discovery, they are bandits. It's just that the action space is not, 1 out of n things. It's combinatorial because you build these pieces. So the action space is not something you can enumerate. So you can't apply the typical bandit algorithms, but a lot of the math is totally applicable. And in fact, what we used in the drug discovery setting is UCB, upper confidence bound objective, to learn a good exploration policy. So that comes out of the bandit research. What it does is it combines the risk and reward, expected reward quantities together in a way that, in theory, guarantees that you will do an efficient exploration and find that where's the money, where's the reward,
Right.
all of the possible places where you can get the reward.
So in the GFlowNet papers, you often describe it as, we want to sample not only the maximum reward path in order to have more diversity, in order to maybe figure out something that we didn't know if we were just to go to the maximum reward. And that speaks a little bit to the things that we know that we don't know, right? We maybe know that, right, this seems like a lower reward trajectory. It might turn out to be a higher reward trajectory. However, exploration in reinforcement learning is also fundamentally addressing the things that I don't know, which is where stuff like random exploration and things like this comes in. Could you maybe comment a little bit on how you see because it seems to me that if I manage to sample according to what I think is the reward distribution, right, I still have this problem of maybe there is a deceptive rewards. There are, I need to take a step back. I may not know some area of the search space. And don't I just run into the same problems again?
So the important trick here is you need your model of the reward distribution or the reward function to be one that captures uncertainty, like maybe in a Bayesian way or whichever way. The Bayesian way, by the way, fits well with the GFlowNet framework because we can consider the parameters of the reward function as latent variables. Like, you don't actually know the reward function. You're trying to figure it out from experiments. So the GFlowNet can sample not just like what you should be doing in order to acquire information, but also potential reward function. So we don't actually have a knowledge of how what's going to be the rewards we're going to get in the world. Classical RL is going, as you said, to the expected value and trying to maximize that, whereas the GFlowNet approach is trying to acquire as much knowledge as possible about the underlying reward function. So you're trying to minimize the uncertainty. So your model, the GFlowNet, is modeling the uncertainty, and then it can use it as a reward for the policy that is going to do action in the real world. Okay, so we're talking about different GFlowNets. There's a GFlowNet that models the uncertainty in the reward that you're going to get from the real world, and that's like a Bayesian model. And then you have another GFlowNet that controls the policy that searches, and its reward is how much uncertainty reduction you're going to get by doing this or that. So yeah, you need to have a part of your model that is kind of aware of the fact that there are whole areas in the world that you don't know about, or aspects of the world that you don't know about, so that it can drive the exploration.
I would love to know where some of the magic is coming from. The promise of GFlowNets is that we can discover as many modes as possible in the path distribution. Traditionally in Markov Chain Monte Carlo, we had to hack priors into the algorithm by hand, to find new modes or areas of information efficiently, especially when they were very far apart or not very sharp. The hypothesis of GFlowNets is that the structure of these modes is learnable on many problems, even in high dimensions. It's a little bit like saying we're getting a free lunch. I mean, actually, I think you used that exact phrase to describe what we're doing here. Many research avenues have tried to develop general methods to discover these structures and have failed. How do you think GFlowNets will overcome this seemingly intractable curse?
There is no guarantee that they will, because if there is no structure in the underlying function you're trying to discover, so let's say the reward function or the energy function that you care about, then having visited some finite number of modes, like regions where your reward is high, say, is not going to tell you anything about what are the other good places, the other modes. So there's no guarantee that it will work. But if there is structure, then there is a free lunch. And we know machine learning is good at that. Like the last 10 years of deep learning and its success, what is it telling us? It's telling us that you can generalize, right? That these nets, I'm not saying they generalize perfectly, but they can generalize. So you can think of it like the machine learning problem is given some examples of good things, like places where you get reward, can you generalize to other places? And the supervised learning way of thinking about it is, given a candidate place, tell me how much reward I think I would get. The GFlowNet sampler is learning the inverse function. It's learning to sample, but it's kind of the same thing. It's just going in the other direction. Give me some, sample some good places that where the reward is high. So we now have a lot of experience in designing powerful neural nets that can be leveraged to generalize in those spaces where we normally use MCMC. And if there is kind of regularities that allow to generalize, then all of that can be put to use.
We mentioned earlier reinforcement learning often being applied in a context where you have this kind of solid reward function. So let's say games, playing chess. I'm really curious, what would happen hypothetically if we applied GFlowNet, to something like chess? So, I mean, I think given the fact that reinforcement learning, like say AlphaZero, is trained specifically to choose the best move rather than diverse moves, it seems obvious that maybe if given equal resources to both AlphaZero and FlowZero, AlphaZero would probably beat FlowZero. However, I think if FlowZero were given more resources, say, and trained to the same rating, say the same ELO rating as AlphaZero, it seems like FlowZero, if you would play significantly more diverse and interesting games with a wider variety of styles. And I think you could even imagine also that it could be possible, even if given equal resources, but sufficiently high enough resources, that a hypothetical FlowZero would consistently reach higher ratings because it might find, more interesting stepping stones that have the potential to avoid deception because it can explore seemingly lower reward paths that ultimately develop into higher reward. I'm more curious if you have any thoughts on that.
Yeah. It's a good question. I would say where the kind of approach we've been pioneering with GFlowNets might be really paying off is if you think about it from the perspective of the learner has a finite computational, amount of resources. Because in principle, right, if you had infinite compute and the reward function, like the rules of chess or Go, then you can just crank and find, the policy that's best in every possible setting. Now, if you have finite resources, like, you have a budget of compute, you'd like to use it efficiently. And so that's where the exploitation trade-off becomes important. And if you had a current policy that you're not completely sure is the right one, and then you're trying to say, well, how should I play so that I'm going to improve my policy the most, as in I'm going to reduce the uncertainty that it is the right policy, like that it picks the right things. So now we're getting closer to the kind of setting where it makes sense to use GFlowNets. And then what I would expect if we do the engineering work here, but based on the sort of much simpler problems we've looked at, is that it would converge faster. So given, if you look at on the x-axis, the number of games you're playing, and on the y-axis, how good is your policy measured like on other games. So that's where you would gain. In other words, it's the learning curve that you might gain on. Asymptotically, everything is going to converge to the optimal chess player, right? So the place where it's interesting is to look at the learning curve, how fast you learn. And here you want a sort of active learning thinking, like, well, I'm not just trying to win here. I'm trying to gather information so that I'll win more in the future. And it's a different objective, right? And that's where you need diversity and exploration and like a model of your own uncertainty and an active learning policy.
Right.
How much do you think this could be part of not maybe only reward maximization things, but information collection things? Like, I'm sure you're thinking about in, let's say, the brain, there's sort of maybe a similar process going on, and what do I still need to retrieve in order to give certain answers to questions? Or maybe in our, let's say, a big search engine, let's just name one for naming's sake, let's Google or so, would try to answer your query, not by just searching through their index, but by actively doing this multiple things, like, is this enough? Is this enough? Is this enough? Do you see connections to these types of things, or are they inherently different because they might be not learning on the spot?
What they're doing on the spot is acquiring information, and you want to do it in an efficient way. That's where sort of the active learning thinking comes in. And I think it's actually a very big practical problem in deployment of like AI dialogue systems that are not chit chat, but are trying to say help a user achieve, get something, get information or something like this. There's a huge need for this in the business world and search engines, and but it's much more than search engines. So I don't think we have the algorithms that do that right now, and it's kind of painful. The humans has to know, is driving, but if we had systems that could explicitly model their own, say, uncertainty about what the user needs or wants, or where to find the information. And then you need like pretty powerful models of that. Like, it's not just Gaussian, they're simple things. That's where GFlowNet strengths comes in. You can represent very, very complex distributions over compositional objects. It's not just a few numbers. Then I think you could get to much more efficient human-machine interfaces. And I believe the same methodology could be used more generally in scientific discovery. So what is scientific discovery? Like, what is it that scientists do? They plan experiments that are going to allow them to reduce the uncertainty on their theories of some aspect of the world. It's the same problem. You have a series of questions you're allowed to ask to nature, and you try to ask as few questions as possible to, as quickly as possible, understand what's going on.
Is there a connection fundamentally to, I'm thinking of causality, which also I've seen a number of papers that you've collaborated on with people who are deep into causality research and so on. What do you think there is a connection there where an agent could learn to uncover, if you think about scientific discovery, to uncover the fundamental causal structure of the world by asking such questions? Like, could there be a connection to that branch of research, and could this finally be like the unification of something machine learning and the world of causality?
Yes, you guys are really asking all the right questions. Thank you so much. In fact, one of my main motivations for pursuing the GFlowNet research program is that I think it's an ideal tool for implementing what I called in my talks system 2 inductive biases. So what this means is there are lots of things we know from neuroscience and cognitive science about how we think, and we can bring that into the design of probabilistic machine learning, based on deep learning as the building blocks. And one of the inductive biases, like one of the characteristics of how we think, is we think causally. We are constantly asking the why questions. We're trying to find explanations and so on. And that connects with classical AI. Like the way we think, to some extent, has also inspired classical AI, rules and logic and reasoning. And we haven't yet found the way to integrate these abilities in deep learning. And of course, lots of people are like trying to, and that's important. But I think the reason why GFlowNets give us an amazing handle on this is because they're really good at representing distributions and sampling over graphs, and like a reasoning or a set of possible reasoning to explain something or to for planning. These are graphs. And your thoughts can be seen as graphs, right? So think of like maybe a simple version of this. Think of a parse, like a semantic and syntactic parse of a sentence is a graph, but usually it's more than a tree. There are all sorts of semantic connections, including with knowledge graphs, right, which are also graphs. So the ability to implicitly represent those distributions and sample pieces of them as thoughts is, I think, fundamental to how we think. And going back to causality, one of the hard questions that I think GFlowNets can help us with is causal discovery. So in other words, what is the underlying causal structure of the world, including the uncertainty about it, given the things we observe? A lot of the research in causality has been, okay, we observe these random variables, discover, make inferences about, what we can say about whether A causes B and so on. But it's much harder to discover the causal graph that in a large set of variables. And it's even harder, and really nobody's done a real job there, to do this when what the learner sees is not the causal variables, but just like low-level pixels. And you also have to figure out what are the causal variables and how they're related causally. And I think GFlowNets can help us do that.
This opens up so many avenues of questions. I think it could probably almost be a future episode in itself. But let me just ask you about some of the basic ones, which is, as you mentioned, kind of learning the causality structure, much more difficult problem. And the first question is just how to represent the causality. And so you mentioned graphs. Graphs is one way, and of course, you can develop isomorphic ways of representing certain parts of logic as graphs, et cetera, depending on how rich you make the graph structure. But there's also the other issue of, when you're trying to build, and I think it's probably correct to call this a world model, right? Like we're trying to build a
yes,
causal.
That's the word I use.
Okay, great. So I have one quick question about that, which is, to me, to some people, a world model is only the discriminative function. It's just that, probability of y given x. To me, it's more general. It's also the structure of x. Is that also your view as well?
Yes.
Okay. And so in constructing those world models, some of the, let's say the pushback on these type of generative techniques from folks that are skew more towards the discriminative side is, hey, look, fine, you're going to go and try and build this generative model. It's going to be even more complicated than this discriminative model because it also has to learn, the structure on X. But I think the possible free lunch here is that you can learn abstract structure on X. And so if you learn these abstract world models, throwing away all the nitty gritty that doesn't really matter, you can potentially have very powerful, predictive encoding, if you will. Like what's your thoughts on that?
Oh, that's what I've been thinking for almost 20 years. And awesome. One of the reasons why I've been interested in deep learning as a way to think of discovering abstract representations, from the early days of deep learning, as in like mid 2005 or something. And in the paper that Jan Lecker and I wrote about, and also other papers I wrote with some of my colleagues at University of Montreal on deep learning around 2010, they are all about that notion that we would like these unsupervised learning procedures to discover these abstract factors, as we call them. But now I think it's not just the factors, like the variables, but it's also, more importantly even, how they're related to each other, which in the causal language is what we call causal mechanisms. Mm-hmm. And so here's a fundamental way of thinking about this. If you don't introduce the abstract kind of structure that exists in the world, then representing P of X, the input distribution, is very difficult. It's in other words, you'll need a lot of data to learn it, and right. It's not going to be generalizing very well. The whole point of abstraction is that it gives you very powerful abilities to generalize to new settings, including out of distribution, which is one of the hottest topics in machine learning right now. How do we extend what we do so that it generalizes well in new settings? And thinking causally about these abstract causal dependencies as the things that are preserved across changes in distribution. Like if I go to the moon, it's the same laws of physics, but the distribution is very different. How do I generalize, across such changes in distribution? It's because the learner is us. If we had the right education, has figured out the underlying, at least enough of the underlying causal mechanisms that we can be transported in a different world, but where it's the same laws of physics, and we can predict what's going to happen, even though it looks completely different from our training environment. So the idea of abstraction is really that if you introduce abstractions, the description length of the data becomes way smaller, and that's why you get generalization.
Absolutely.
I'm fascinated by these abstract categories. I think it's the most exciting thing in AI. I mean, Douglas Hofstadter spoke about cognitive categories, like the concept of sour grapes, for example, to represent a certain thing. And almost magically, our brain seems to arrange these cognitive categories. And it's not entirely clear to me whether they're an emergent phenomenon or whether it's some other process. But the modes that you're discovering in GFlowNets, they're a kind of category. These cognitive categories that I just spoke about are abstractions. Also things like causality and geometric deep learning, they are kinds of categories. But I've always had this intuition that deep learning doesn't learn the categories on its own. It needs humans to kind of put priors into the model, as we do with geometric deep learning. Do you think that will always be the case, or can we have that meta level of learning?
Yes. What I really want to do is build machines that can discover their own semantic categories, abstract ones that really help them understand the world. And of course, they're going to learn, better and faster if we help them, just like, we teach kids. We don't let them discover the world by themselves. But we do have an ability to invent new categories. That's what scientists do all the time, right? Or artists and writers and philosophers and scholars and ordinary people who find new solutions to problems. We do that all the time. Our brain is a machine that discovers new abstractions. Of course, usually it's just like one little bit on top of all the things we got from our cultural input. But that's the ability that we don't have right now in machine learning, and that is going to, I think, be a huge advantage. So now we're not in reinforcement learning, we're not in active learning, we're talking about unsupervised learning. So we're talking about how can a machine discover these often discrete concepts that somehow help it understand. So in other words, build a compact understanding of lots of things that generalize across many settings. And that's the path to build that is becoming more and more firm in my mind as I move forward with GFlowNets. So as a clue, there was a paper we had recently, I think in Europe, on that's connected to the global workspace theory that says that it's about discrete valued neural communication, I think is the title, where the one interesting intuition here that's connected to this is if you constrain the communication between different modules, say in the brain or in the machine learning system, to use as few bits as possible, and discrete is the way to get with very few bits, you can get better generalization. And there are good reasons for that we try to explain in the paper. But that's it. There's a clue here that discrete concepts emerge as a way to get better generalization.
You mentioned before, and in terms of discreteness, and what you mentioned before with graphs being very fundamental, it connects a little bit back to a paper that you, I think, provocatively titled "The Consciousness Prior," where you connect sort of the ideas of attention, sparse factor graphs, language, things being discrete, things being describable by a language, right? And I find that all to be very interesting. On the topic of consciousness, we would be, it would not be appropriate for us to not put this question to you. So you're not very active on Twitter, which is probably why you're so productive. But if currently there is a bit of a thing happening on Twitter, namely Ilya Sutskever of OpenAI has tweeted out a seemingly innocuous tweet saying, it may be that today's large neural networks are slightly conscious, which has resulted in quite a, let's say, a storm of people agreeing, disagreeing. Obviously, he's talking about maybe, the large language models we have today, which do incorporate a lot of the things you talk about. They do incorporate attention mechanisms, lots of them. Presumably, it's all one needs. They do incorporate language. They do incorporate discrete things with, discrete tokens and so on. What do you make of a statement like this? It may be that today's large neural networks are slightly conscious.
Well, there's one fundamental problem with such statements, which is we don't know what consciousness really is. So I think we have to have a bit of humility here. I can't say what Ilya is saying is true or not. I think that there's more to consciousness than what we have in these large language models by a big gap. But that being said, and we do need to work with our colleagues in neuroscience and cognitive science who are trying to figure out what consciousness is from a scientific perspective, and philosophers who are helping also to make sense of that landscape. We have to be careful with the use of those words. And, I was a bit literal in the title of my paper. And I learned a lot about consciousness since then. I learned that there's a lot that we don't understand. That at the same time, there are enough bits that we know from cognitive neuroscience that can serve as inspiration for how we could build machine learning systems that have similar, say, conscious processing machinery. Okay, let's not say consciousness, but just conscious processing machinery, because that's less controversial. And by the way, the word consciousness has been taboo in most of science for a long time, and it has become detabooed in neuroscience because we're starting to be able to make measurements of what's going on inside your brain while you're doing things consciously or not, and so on, and distinguish the parts that you're consciously aware of and the parts that are there in your brain, but you're not conscious. So we're starting to make a lot of progress on what it means to be conscious of something or not. I think this is a very exciting and important scientific question. And I would rather work on exploring hypotheses and theories to explain our conscious abilities, rather than make bold statements about whether current neural nets are conscious or not.
Professor Bengio, we've got David Chalmers on the show next month. Do you have any questions that you would put to him?
I very much like a hypothesis about consciousness that Michael Graziano has put out to help explain the qualia, the subjective experience part that Chalmers wrote might be something science can't really, touch. And so I'd like to hear what he has to say about these kinds of approaches. And one of the basic premise here is it is very grounded in things we can do scientifically. It's to say, well, let's not try to figure out what is consciousness or subjective experience, more specifically, from a philosopher's chairs, but let's consider that as a phenomenon that is happening in the brain. I mean, unless you believe in sort of supernatural things, it is happening. Something is happening in the brain, and we can report about it, and we can measure what's going on in various parts of your brain while this is happening. And then, can we then come up with theories that explain why we feel that we have subjective experience. It's not saying whether consciousness exists or not, or subjective. It's not whether it exists or not in some sort of philosophical sense. It's whether, what is it that's going on in our brain that gives us that feeling, and then make us say, well, I'm conscious of X, Y, or Z. So that's the direction I find interesting, because it opens the door for scientific investigation. And Michael Graziano has a specific theory about that, which I find compelling, that is really rooted in the idea that we have a world model, and then we because we have an attention that focuses only parts of it at a time, and we need to have like a little mini world model that controls that attention, that creates a sort of separation between the where the real knowledge is, and sort of this more abstract control machinery that could well give us this illusion of Cartesian dualism, which I think is an illusion, but must be grounded in some biological a reality. And that's, I think, understanding that is a very good question to ask. And I'd like to get to know what he thinks about such a research program.
Thank you very much.
Very cool. Yeah, thank you. I do have one kind of nitty-gritty question, because, and partly based on some of your recent work, I'm becoming more of a fan of semi-supervised learning. And, you had a recent paper that was on interpolation consistency training. And what I found interesting about that is that if we consider one of the biggest challenges that we face in machine learning pretty much across the board is in overcoming the various, curses, if you will, the various forms of intractability that we have in empirical learning methods. And in this context of semi-supervised learning, that recent paper, it found significant improvements over state-of-the-art by forcing linearity. So in this case, it was by this mix-up between the unlabeled samples and their interpolated fake labels. And in the last decade, we've also seen ReLUs come to dominance in the field of neural networks. They're piecewise linear. Recent work by Randall Bellistriero developed an interesting frame of reference which cast multi-layer perceptrons as a decomposition method, which produces a honeycomb of linear cells in the ambient space, and they're activated, turned off or on by input examples. So my question is, why is linearity, whether it's piecewise or otherwise, dominating the state of the art in approximation methods? It almost seems to me like we've kind of gone back to the future, if you will, sort of leaving behind attempts at more smooth, nonlinear methods and gone back to newer, albeit more complicated forms of linear approximation.
Right. I would say something that's roughly linear is simpler. Right. So having a regularizer that says, oh, you want to be roughly linear or locally linear, at least to as much extent as you can, is a smoothness prior. Right. So that's going to help generalization, but it could also hurt if that is too strong. And so having these piecewise linear kind of more type of solution is a good compromise. It says as few pieces as possible, and ideally organized in a compositional way, so that it's not just like a ReLU. It's more like the discrete abstract logic, reasoning thing sitting on top that's controlling the pieces. But otherwise fairly simple in how each of the pieces are, like linear, for example. So one way to look at this is, if you look at classical, the kind of rules that classical AI researchers were using, each rule is fairly simple. It's like it's almost linear, or it's very simple logic. But it's the composition of all those rules that gives the power of expression of these systems. Of course, the problem then is that they didn't know how to train them properly. I think I think we learn to come up with these discrete ways of breaking up things into simpler pieces. And that, in fact, I think if you're Bayesian about it, it just comes out naturally, and they're very, very weak assumptions.
Mm-hmm. So in a way, it's almost, it is piecewise abstraction. So we're really kind of back to...
Yes, that's what I would lean to rather than piecewise linear. But linear, of course, is a broad part of, it's an easy way to get simple.
Amazing. Professor Bengio, I'm interested in your personal journey. So we've been talking about diverse trajectories, and I wanted to know about your own trajectory of research over the last 10 years. Now, one of my mates, a psychologist and symbolist, Professor Gary Marcus, presumably one of your best friends, by the way, he pointed out in his 2012 New Yorker article that MLPs lacked ways of representing causal relationships, such as between diseases and their symptoms. And I think this has been a significant focus of yours in recent years, as we've discussed. And he thought at the time that you were a bit too, quote, system one all the way. And he spoke then about the need for heterogeneous architectures and the acquisition of abstract concepts, compositionality and extrapolation, which I think has also been a huge focus of yours in the last decade or so. We really enjoyed watching your debate with Marcus. And by the way, we would love to host V2 of that debate. So if you're interested, you just let us know and we'll do that. But he's often viewed as a heretic. And just forgetting about symbols versus neural networks for a minute, am I right in thinking that you've converged in at least some ways in your thinking? And how would you characterize that from your perspective?
So, yeah, I used to be in the 90s pure neural net sub-symbolic connectionist researcher. And I did my grad studies at a time on neural nets, at a time when the dominant way of thinking was these, classical AI rule-based system with no learning at all. And it was dominant, meaning that the little group, like, Jan and Jeff and I and others who were thinking otherwise had to, defend our views. And maybe that led to a kind of, us versus them, I think, unhealthy way of thinking. And of course, I've matured. And one of the big, I think there are several turning points on that journey. One of them in the 2000s was the realization of the importance of abstraction. So, and the way to think about this maybe more concretely, because what does it mean to be abstract, is that I was thinking, well, what would be the right kind of representation we want to have at the top level of our unsupervised deep nets? Because we were doing mostly like unsupervised deep nets, like, deep Boltzmann machines and stuff in that decade. And I was thinking, well, it would be things like words, right? Things like the sort of concepts that we manipulate at the top level. Well, it's words, or, the equivalent maybe with disambiguated. But yeah, it didn't seem that we have the right tools for that. And then it remained like an objective. And then in 2014, we discovered the power of attention. And that's closely connected to abstraction, because what it does is it focuses on a few things. And of course, that's very much a characteristic of how we think. A thought has very few elements in it. That means we have selected those elements, and that's where attention comes in. So it's getting closer to this ideal of building machines that think like humans. And then, of course, in 2017, I wrote this consciousness prior paper where, I discovered all the work on global workspace theory, and it and the momentum is built up. And of course, now, humans think and they use symbols and they understand the very abstract relationships between them. And we need to build neural nets that can do that. So I guess where I've maybe departed from Gary, but maybe he's moved to, is it's going to be neural nets that do it, right? It's just that we're going to be training them in a special way. And that's what GFlowNets really aiming at.
So can I just say, we ask many guests these questions about their evolution, and sometimes they tend to be spicier than others. But I have to say, from my perspective, your answer was the most informative, the most gracious, and the most noble of answers that we've heard so far to similar questions. So kudos to you. That was awesome.
Thanks.
I just cannot believe it. And we always do a hell of a lot of preparation, but it's got to the point now where we know that we're not going to get more than about 6 questions in. So we kind of like exponentially, we have an exponential prior on our questions.
Well, he was awesome though with we asked him to give relatively sort of 3-minute answers and he stuck to that, which was really cool. I mean, that's very helpful to have an interesting dialogue. And I can't believe how proud I am, that he appreciates that we put the prep time into it and, had decent questions that were hopefully interesting for him as well as our audience.
So, Dr. Kilcher, Lightspeed Kilcher, what's your take?
It's cool. I think the thing he mentioned at the end, like his humility, it kind of shines through everything he does, and he answers. He's like, here's the best answer I can give. But he seems to be very like open and not very. Yeah. One notices he's not on Twitter. It's like, it's noticeable.
That was a brilliant question. I think we should post that question on our Twitter. Because, there's that, a bit for people watching this in a year's time, it's probably forgotten about. But yeah, that Ilya guy from OpenAI said that the models might be slightly conscious. I was exasperated by that because I watched his interview on Lex, and I know by saying bad things about him, he'll never come on our podcast, but I don't think he would have done anyway, so it doesn't matter. But I think that it's pretty bad.
Why?
What exasperated you?
Why? It's like.
Oh, you don't think it's bad? What's
no.
Up?
He says like.
I think because a lot of the folks at OpenAI, they are like in the rationalist community, and they seriously believe that we're in imminent threat of the AI taking over the world and us being paper clips. And I think it's next. I listened to his interview on Lex, and he sounded like a salesman talking about Codex and how it was going to revolutionize everything. And I honestly think that there's just such a divergence between what they're saying and reality right now.
Well, not to drift too far away from our guests today, but so I thought it was just kind of a shower thought, the large neural networks of today might be a little bit conscious, right? And you're just like,
a shower thought.
And it is a shower thought. Like, it's on Twitter. It's just something you tweet out, and it brings up interesting questions. Like, it brings up interesting questions. Like, you're a ball of neurons. Like, you're just a slapped together piece of matter, right? You have consciousness. So clearly, like, something about, learning systems combined with data, or maybe not even combined with data, gives rise to consciousness. So why can't another, in silico slapped together system of neurons ingested with data be slightly conscious or have like some properties? Like, and that's essentially, Bengio refused to give like a humble person he is. He refused to give like the strong take on that, but that would have, because he might just, this is my opinion, not his obviously, but reading the consciousness prior paper, it is not too far off. He formulates consciousness as having these elements of, I have my internal state, which is sort of everything in my brain that I could bring up into my forefront. Then I get some input from the outside world, and through the input, I then filter, like with an attention mechanism. I look what in my mind could I now bring into focus, right? And that is by use of something like an attention mechanism. And then I take that thing and I put it into these abstract concepts. I represent the concepts in my head as a sparse factor graph, and by focusing on parts of that, I can then make inferences in this sparse factor graph and so on. Now, obviously, something like GPT-3 doesn't have all of that, at least not explicitly, but some of it is there, right? It's, I have a piece of input, I have giant amount of weights. I use an attention mechanism to sort of see what I can focus on.
Yeah, but
I think that's a very declarative description of consciousness, and at its roots, it's about the phenomenological experience, right? And I know we discussed computationalism and panpsychism. Let's not go down that rabbit hole. But surely they don't think that this model can feel.
Well, but so this is
consciousness is not about feeling.
Yeah,
it's about being like aware of like I don't even know what it is. I'm just saying that it sounded not too far away from what the consciousness prior paper was about. And so yes, I realize it's called the consciousness prior and not consciousness, but you know.
Yeah, I mean, I think he answered it the way a scientist should answer it. And I was really happy with his answer, which is, okay, A, consciousness has to be some activity of neurons and firings or whatever in the brain, or else we're talking about magic, and that's not in the field of science. And B, whatever that thing is, it's obviously quite nuanced and complicated, and we don't know yet. So we need to have some humility here, which means we shouldn't be alarmist. So we don't need to be going and burning books tomorrow because we created a GPT whatever that anytime its wheel is spinning and it's actually suffering. If you ask it a question that's too hard and it's spinning, it's because you're hurting it and it's suffering, and so we need to turn it off like right away. But wait, we can't turn it off because then we'd be like murdering a sentient being or something. Like we're way too in our infantile understanding of this type of complex behavior that's the human mind and consciousness to be at that point. So from my perspective, he answered it completely 100% scientifically, and there's a lot of folks out there who are supposed to be scientists that spend a lot of time with unscientific thinking about it.
Cool. Let's talk. One of the things that I really found interesting about Bengio's ideas, other than the causality stuff and the system 2 stuff, is this notion of diversity. We've had conversations with Kenneth Stanley all about open-endedness and diversity preservation. We've also had conversations with Friston about the importance of balancing relative entropy and so on. And we have all of these curses in empirical learning, right? The statistical curses, the approximation curses.
Dimensionality. We have to mention dimensionality.
Dimensionality, and even, I mean, we're talking about curses in the Monte, the Markov Chain Monte Carlo in the sense of it being a high dimensional space, and we need to assume that there's some structure around where these modes are. So all of these approaches are ways of simultaneously, being able to explore but not being cursed. So yeah, what's your take on that?
Well,
you?
My take was that I like that he's so interested in abstraction because to me that's been not only it's not only one of the larger mysteries, at least for me. I mean, I don't know, of the kind of the universe is abstraction, idealism, Platonic thinking, whatever. I mean, the whole point is just that he views abstraction as a key to pragmatically useful paths forward. And it's a hard problem, a really hard problem. And, his focus right now is on kind of graph-based structures. And I have to admit, for me too, they're quite seductive and appealing. I don't know if they're the right path forward, but it's definitely cool to see a lot of research looking into graph-based, methods, or, hypergraph-based methods, whatever they are. They seem to definitely be a promising path forward. And I think we're in for, hopefully, if we can continue to progress at a reasonable rate, some interesting decades ahead.
I mean, I would also postulate that maybe most of our, let's say, benchmarks that we're thinking about today aren't necessarily suited to because his argument was by creating abstractions, it might actually, help your ability to learn something, right? Which is a thing that we all intuitively understand in the world. If I have good abstractions, I can transfer my knowledge from here to here and from here to here. Yet in something like ImageNet classification or whatnot, or most of the benchmarks we have today, the necessity of abstractions is probably not like the data, the hardness of the problem probably doesn't require abstractions to be introduced. And therefore, the limiting factor here might not only be the models themselves, but also, let's say, our ability to even measure the progress one could make with abstractions. And I think that's going to change maybe in the near future, because people are going into multimodality research and so on. And there, I think the concept of sort of concepts, maybe not abstractions, but at least something like concepts is way more important.
Yeah, and there's let me just follow up real quickly there, Tim, because there's something very interesting there to Yannick, which is the lack of good tools to deal with multimodal, sets of data results in a lot of times we're just throwing out kind of valuable sources of data just because, we don't have a good tool set to do with them. Like, think about the self-driving car, like the whole should it be vision versus LiDAR debate. Why isn't it both? I mean, if you can, for $5, you can throw on some cheap, LiDAR sensors or something, maybe not something fancy, but something cheap. Why wouldn't we take advantage of that data? And it's really because we don't have good tools to deal with multimodal data.
We got to a good point in the discussion where we were talking about the nature of finding abstractions. And I wonder whether neural networks can find abstractions. Now, the cynical view is that humans kind of create these inductive priors and they represent the abstraction. So certainly in the case of geometric deep learning, and that's kind of what's happening. We put the priors in there to reduce the size of the approximation space. And Keith and I had an interesting idea yesterday that there's a kind of analogy between geometric deep learning and causal representation learning. So I think, Keith, you went online and you found a really interesting definition of a causal model, which is that it's kind of immune to, let's say, adversarial examples. So what a model does right now is it learns a relationship essentially between, let's say, every single pixel and something happening, right? Which is why that model is vulnerable.
Yeah, so that was and Yannick, would love to get your comment on that, but that was, this paper, and I could go dig it up, but I'm not going to get the reference right now, where it said, hey, what is the difference between a causal or a prediction from a causal model versus a prediction from a non-causal model? And the point was that, well, almost by definition, really, if you have a causal model, then if you perturb the inputs, the prediction that you get out of it remains a valid output, because after all, if it's a causal model and it's reflective of sort of the causal structure of the world or whatnot, then sure, that's a valid output. Whereas if it's non-causal, it has the potential to learn all these kind of spurious structures, and therefore that's why you get the capability of these adversarial examples where you just, put a little rainbow pixel somewhere and it messes up the class because it had the spurious connection.
I mean, in the same vein, you could also, the adversarial examples are there because of inaccuracies, because we don't have the perfect discriminative function, right? I could also say, well, if I just had the correct discriminative functions, it doesn't need to be causal. If I just had like the right partitioning of my input space, then, I'm super not vulnerable to adversarial attacks. I guess the real question would be, would that technically amount to a causal model if I had, the perfect partitioning of the input space into my classes? I don't know. That's like, is there like a mathematical equivalent from that to a causal model? Who knows?
Right. Yeah, I think there's probably, it's probably, certainly, if you had the perfect discriminative function, it's probably the discriminative function that you would derive from a causal model. Yeah. I'm not 100% sure you can go in the reverse, because I imagine there probably is some information loss going from, a causal model to, like, for example, I'll give you an example. In the cases of, say, production systems, so these little rewriting rules or whatever, the definition there of a causal system is one in which all the potential graphs, all the potential transition graphs that you can get to a particular output are isomorphic. So even though you can have like the perfect discriminative kind of function, there may be multiple possible graphs that you could have gotten there, but they're isomorphic. So I'm not quite sure, how that would translate into this point. Yeah. But I think you'd be just as good for the purpose of discriminating.
I think it's related to the semantics discussion we're having in NLP. So people like Walid Sabah say that neural networks don't have semantics. And in the same way as I was just saying, blue pixels, I mean, in the real world, let's say male testosterone levels is causally linked to incidents of car crashes, which means you can now take the model in Holland, in a different country, and because it's a causal factor, it will extrapolate in the same way. But neural networks models, because what a human does is we would come up with the right representational abstraction. We would build a model, which is very reductionist. A neural network models everything to everything, and the semantics are all one thing.
Well, okay, I'm not too keen on discussing like semantics and whatnot with NLP people, but I would.
Why not?
I don't know.
Sounds interesting.
Like I don't know. It often veers away, and
it veers into semantics.
It's like it's a bit too.
It veers into semantics.
I like what I think Connor Leahy said, like when we talked to him
he wouldn't like that
when
either.
we talked to him a long time ago, and I happen to agree with him there, is that you sort of have to see everything from the perspective of these models. Like if I'm a GPT-3, my entire world is text input, right? And people can't somehow judge GPT-3 by, well, you don't even have a connection to the real world. You don't even know that you don't go see a doctor if your plant is sick, right? Like, how can you not know that? Like, okay, they don't live in the real world. They live in the text world of the internet. And in that world, I'm not sure if there is not a level of abstraction happening in these models. Like, I don't want to claim that these things do not form abstract things. It might not be the same abstract classes that we form, but they definitely form some level of abstraction. And of course, they can't transfer it because we only give them the one modality, right? But they may be able to transfer it between, different areas of text, which they sometimes do, right? And so that's, I just wouldn't be so conclusive with respect to these things.
That's true. I think we've gone full circle now. So after speaking with Randall Balistriero about the splines, that almost results in such a cynical reading of MLPs that they're just hash tables. But we're not using MLPs, we're using transformers and we're using CNNs. And actually, if you think of abstraction just as being extrapolation, I think they are basically synonymous. It's about being able to extrapolate outside of your training set. Then those inductive priors are indeed producing abstractions. But the problem is humans design those inductive priors. What we want is to learn abstractions. And that's the thing that I don't think is happening.
I'm kind of on the same page as Yannick and Connor on the one hand, which is, hey, if an abstraction is just a compression, encoding of the input space, then of course they're learning abstractions, right? I mean, they are throwing away, information and retaining some abstract thing. I think that just kind of devolves into somewhat like bastardization, if you will, of what people mean when they say abstractions, because the types of abstractions that traditionally we think about as abstractions are simplifications. They're like simplifications of more general, longer range kind of structures, whereas we know, and I think we all know this for sure, that a lot of the quote unquote abstractions that a neural network learns are these kind of like shortcuts, right? They're like these low level, borderline, spurious kinds of abstractions, and that's why they break so easy. That's why they're so brittle. And I mean, there is this vagueness here, right? Like, when is an abstraction a good abstraction? I don't know, but I think it all kind of, in a way, misses the point. Like, what we're talking about here is that, and this is a lot of what Bengio said, right? Which is that the goal here is to figure out how to get machine learning to learn structures that, by virtue of their simplification, their simple abstractions, are more generalizable out of distribution, right? Like, that's really kind of the goal here. And I mean, so the rest of it is just semantics, pun intended.
I mean, if you look across the world, a lot of, let's say, cultures and humans and so on must have the same abstractions, right? So it must mean a little bit that it's not just something you learn during your lifetime, right? So, right?
Oh, absolutely not. Yeah, correct. It's learned by evolution, by the species, by life itself.
Exactly, right. But is like the analogy to us building in the correct ones as a shortcut for just evolution doing it using essentially random search, right? That is, it might, right? It's a different quality of, we want machines to learn something, because usually we think of, when we say we want machines to learn something, is we want them to ingest data akin to maybe what a human does during its lifetime. But these sort of abstractions and the ability to form abstractions, they seem to be happening on a more fundamental shared level.
Yes, you just put the pin in the center of the bullseye. I think that's exactly right. There's a lot to be said for, I mean, it's an epiphenomenon, and a lot of intelligence is embodied. And I agree that there's an awful lot of stuff going on unbeknown to us. There's clearly something that most people don't have a grasp on.
Maybe this is why
at the population level.
Maybe this is why I'm frequently miscommunicating with people, because I never assumed that learning was about, what a human being learns in a human being's lifetime. Like, to me, it's always been the evolution, paradigm. It's like, what's encoded in your neurons, what's encoded in your DNA, what was learned by bacteria a long time ago, and how did that translate into what human beings are doing. So I don't know why so many people are focused on what a human being learns in their lifetime. I mean, it's more, why is that the goal? I'm not sure.
I know, but we run the risk of being very reductionist, because Conor Leahy said that it's an open question whether humans are even intelligent. And if you go down that line, very quickly you start saying, oh, human beings are just hash tables like GPT-3. Clearly humans are intelligent in some way.
Well, you can just take it as a, matter of definition, but it's not a binary thing. Like, again, why are we always into this black and white concept? Something is or is not intelligent. Like, that's not how I view things. I think there's a spectrum of intelligence from like 0 to, I don't know, maybe infinity or something, some really large number beyond what human beings are. And so it's this continuum. So that's why I like Chalet's kind of on the measure of intelligence, because even though it doesn't actually give us a, quantitative way yet to measure intelligence, it at least is thinking along the right directions, which is, how do you measure intelligence and how do you define it as a category of activity? And then we can kind of get past this black and white, thinking.
Mm-hmm. Well, gentlemen, always a pleasure.
Absolutely.
Yeah, absolutely.